Hello, everybody. Our 14th summer school on geometry is continuing with Federico on calibrated submanifolds.
Thank you. Thank you for the introduction. So today I will be talking about calibrated submanifolds of the Bryan and Salomon manifolds. So this is going to be based on some work by Spiro Karagiannis, Mongminu, Jason Lotte, and Kavaru Kavai, and myself. These are all independent works and combination of the people I told you. So before I go into how to construct calibrated manifolds of the Bryan and Salomon manifolds, let me recall that the G2 manifold is a 7-dimensional manifold with a special structure. We have a free form and a full form, which are closed and co-closed. And so on top of being closed and co-closed, they have co-mass less or equal than 1. So this is the condition, the co-mass condition here. And so in particular are calibrations, and the calibrated submanifolds are called associatives, the one with respect to phi at least, and co-associatives, the one calibrated by star phi. And we also proven at the end of the first lecture that being associative is equivalent to require that this full form restricted to sigma vanishes and this free form restricted to sigma vanishes for associatives and co-associative respectively. So spin 7 manifolds are in a very similar way 8-dimensional manifolds with a four forms form which is closed and with co-mass less or equal than 1. So it's a calibration, and the calibrated submanifolds are called Cayley's. We can also, once again, characterize the being calibrated with the vanishing of a two form, which is this two form here. Okay. The Bryan and Salomon manifolds are, let me recall, that are these 7-dimensional and 8-dimensional manifolds that are constructed as vector bundles over some lower dimensional manifolds. So we have X, which is a n minus k dimensional manifold, and we're considering a k-dimensional vector bundle over k, which is Euclidean, so it has a linear product and has a connection with connection form rho. So the idea is that if I have a local orthonormal frame of X with dual coframe B0, Bn minus k, then I can also construct the local trivializations, and the fibers are then parameterized by A0 k. So in such a way, I have a local coordinates frame for my 7 or 8-dimensional manifold. And like the connection form that I have on my vector bundle implies that the tangent space and the cotangent space, they both split into an horizontal part and a vertical part. The horizontal part can be characterized by this equation here. So we pick the element of the local orthonormal frame and we subtract this connection term. And the vertical space is just spanned by the derivative of these local coordinates A0, AK. And by duality, you can check that the cotangent space splits into the horizontal part, which is just spanned by the local orthonormal coframe of X, and the vertical part is spanned by these one forms here. So in particular, in the case of our interest, we will be working on S3 times R4 with the spin connection. So S3 times R4 is a trivial bundle over S3, and the spinor bundle over S3 is also trivial, so we can identify these as the spinor bundle So by what I said before, the tangent space splits into an horizontal part and a vertical part, and you can write explicitly the free form as u cube times the volume of the horizontal part plus uv square sum over I of bi, which omega I, and the omega I are the anti-self-dual two forms on the vertical space. So u and v are functions of the distance from the zero section. So all it matters to know is that we have constructed the free forms very explicitly, and the automorphism of this Bryan and Salomon manifold is a C2 cube. The second Bryan and Salomon example is the anti-self-dual two forms over X4, where X4 is either the sphere or CP2. Of course, we have a connection, which is the one induced from the Levi-Civita connection, and so the tangent space splits again into horizontal and vertical parts, and the free form is once again explicitly written in this way. Ci are the vertical coframe. And yeah, the automorphism group of such a manifold is SO5, and here I'm just considering X4 equal to S4. The last example is the spin 7-1, and it's the negative spinor bundle over S4. So once again, connection on some vector bundles, so the tangent space splits, and the full form can be written explicitly as volume of the horizontal space up to conformal change of metric, and the volume of the vertical space up to another conformal change of metric, plus the mixer involving anti-self-dual two forms of the vertical and horizontal space. Yeah, once again, the automorphism is quite big. It's SP2 times SP1, and as I mentioned in the previous lecture, SP2 should be thought of as the double lift of the SO5 action on S4, and SP1 only acting on the fiber. Okay, so this is just all we are going to need from the previous lecture. So if you recall what I told you on Tuesday, that's great. Otherwise, this is all you need to remember. Okay, so now we're finally going into some real research from the last 10 years at least. So our goal today is to construct calibrated submanifolds of such manifolds. And the ideas that we're going to exploit are the following. So we know that the Bryan and Salomon manifolds are vector bundles over some base space. So the first idea is to exploit such a vector bundle structure and consider submanifolds that are vector subbundles of M over some submanifolds of the base. And the second idea that we're going to exploit is we've seen that the Bryan and Salomon manifolds have big symmetry group, so we can consider some co-homogeneity one action that makes, so we're going to look for submanifolds that are invariant under some co-homogeneity one subgroup of the automorphism group. Okay. So let's start with the first idea. So we're going to construct calibrated submanifolds via vector subbundles. So we have the Bryan and Salomon manifolds that once again is some vector bundle over some base space X, and we consider LP to be a submanifold of my base X. So, and over this submanifold, we want to construct our submanifold of the ambient manifold Mn as some vector subbundle. So we're going essentially we're decomposing the submanifold as some submanifold times subspace of the vector space. This is going to be clear in a second. But so the trivial cases are when the submanifold is zero-dimensional. So if we assume that P is equal to 0, then LP must be a point or a collection of points. And so all what we're looking at is some fibers of the Bryan and Salomon manifold. So you can check quite easily that in the S3 times R4 case, the tangent space of your fiber, which is diffeomorphic to R4, is spanned by dA0, dA1, dA2, dA3. And so if you plug them into the free form, you see that this vanishes. And so F needs to be a co-associative submanifold. So all the fibers of the Bryan and Salomon S3 times R4 manifold, so R4 times any point of S3 is a co-associative submanifold. In a exactly in the same way, if you pick the fiber of lambda 2 minus of S4, so you're just looking at one point of S4 and the and the fiber of this bundle, then the tangent space is once again spanned by dA1, dA2, and dA3, and we satisfy the associative condition here. And so these are all associatives. And the exact same thing works for the negative spinor bundle of S4. So just to sum up what I said in this slide, this projection map from M to X endowed with the Bryan and Salomon manifold, the fibers of these smooth map are calibrated submanifolds, so of the right dimension. Any question on this very easy construction? Okay, so then let's go on to another trivial example, which is the case where P is equal to K. So we're looking essentially at the zero section of the Bryan and Salomon manifolds.
May I ask
and we
something?
can, yeah.
Is there a natural compactification of these spaces, or maybe by conformal scaling, or I don't know. I mean, it's like, is there such a construction? I just wonder.
Of the Bryan and Salomon manifolds?
Yes, compactifying somehow.
So they're asymptotically conical. So you would, I don't think there is a natural way to make them compact, at least in a G2 way or in a spin 7 way.
Yeah, then structure is gonna change, probably, yeah. But you can make it into a cone, right? So it's
well, they're growing, so it's a cone. It's getting bigger and bigger in infinity.
Okay.
So I don't see how yeah, I don't see how you can do it. And I don't think that, I mean, at least in the G2 world, there is no way to compactify these spaces naturally.
All right. Thank you.
Thank you for your question. But yeah, so I was saying that the base space of these Bryan and Salomon manifolds are also calibrated. And in fact, you can see that S3 times 0 has tangent space spanned by E1, E2, and E3. And so they satisfy the associative condition, so they're associative. And once again, lambda 2 minus of X4, if you see X4 as the zero section of this vector bundle, the tangent space is spanned by these vectors, and this is a co-associative. And finally, on the Bryan and Salomon manifolds over the negative spinor bundle of S4, the zero section, so S4 is as tangent space spanned by these vectors here, and so you can check quite easily that that it is scaling. Something actually stronger can be said in this context, and this is due to Tsai and Wang. What they've proven was that if you're looking for a compact minimal submanifolds of the Bryan and Salomon manifold, then you need to be contained in the zero section. And the reason is the distance function from the zero section is some convex function. And so if you're minimal, you have some barrier argument that tells you that you need to be contained in the zero section. So what is the consequence of such a theorem is that these are all the compact associatives, cross-associatives, and Cayley's in the Brown and Salomon manifolds. So if you're looking for other compact examples, you will fail. Okay, so this was the trivial cases. Something more interesting is when we pick p equal to 1. So if we pick p equal to 1, what we're forced to do is look at S3 times R4. And so what we do is to look at a curve in S3, and at each point of the curve, we have a two-dimensional linear subspace of R4. So this is what our ansatz is telling us. So what I proven with Ben Aslan last year was that for every GTSS gamma in S3, then there exists a unique plane W such that gamma times W contained in S3 times R4 is associative. And conversely, if you pick any 2D plane in R4 and any point of S3, then there exists a unique geodesic gamma in S3 such that gamma times W is an associative plane space. Okay, the proof of this fact is quite straightforward. So I will do it here. So using the symmetries of the space, we can assume without a lot of generality that gamma is a one-parameter subgroup of S3, which is given by the exponential of TA1. And we pick the plane to be just the third and fourth components of R4 to be 0. And so the tangent space of such a manifold is spanned by E1, of course, and DA0, DA1. Now what we need to check is that star phi of E1, DA0, DA1 is equal to 0, and this would imply that gamma times W is associative. So you could do that just by plugging in these vectors in the explicit formula, but it's easier to just rewrite your E1 in its horizontal lift. So the horizontal lift of E1 is precisely given by E1 plus 1/2 A1 D0 minus A0 D1, blah, blah, blah. And so the tangent space of gamma times W is in reality spanned by the horizontal lift of E1, D0, D1, because we are restricting ourselves to the case where A2 and A3 is equal to 0, so these last two terms vanish. So now you can just look at the formula for phi and convince yourself that that star phi restricted to such these three elements is going to give you 0. Any questions on this proof? Okay, so the last the remaining case, well, there are two remaining cases, but they are both concerning p equal to 2. So we are looking at a oriented surface in X4, and such a and from such an oriented surface in X4, we need to construct a subbundle over L of this anti-subdual bundle. The way to do it is by picking a oriented adapted local orthonormal frame. So E0 and E1 are tangent to L, and nu0 and nu1 are normal to L. And so we can, of course, also construct the dual frame B0, B1, D0, D1, which are the dual to L and to A0, A1 and nu0 and nu1, respectively. So we have this adapted frame of L and inside of X4. And from this, we can, of course, construct the anti-self-dual two forms, omega-1, omega-2, and omega-3. And observe that omega-1 can be written as the volume of L minus star the volume of L. So the bundle defined by the span of omega-1 over L is in reality a vector subbundle of lambda2 minus restricted to L. So it's a globally defined object, sigma 3. And in the same way, N4 given by the orthogonal to omega-1 gives you another vector subbundle of lambda2 minus over some submanifold L. Okay, so the theorem that I would like to state and prove is due to Spiro and Minu in 2005. So what they proven was that sigma constructed as above is associative if and only if L2 is a minimal submanifold of X4. So if you pick your favorite surface, minimal surface in X4, then you can construct an associative in lambda2 minus by this construction here. And similarly, if you consider N4 as above, that is co-associative, if and only if the surface that you considered is superminimal in X4. And superminimal is just a stronger condition on the second fundamental form. I won't talk about it today. So the proof of this fact is quite easy in reality. So I will just do it. So if we consider the local autonomous frame above E0, E1, E0, and U1 with dual frame B0, B1, D0, D1, then as usual we have omega-1, omega-2, omega-3. Local orthogonal to realization of the bundle, and so local coordinates and vertical space D1, D2, D3. Now it is clear that first of all, recall that the connection of the anti-self-dual bundle in this frame is just given by rho, where rho is characterized by the Levi-Civita connection of X4 via this formula. So this is just telling you how this rho I, the connection of the anti-self-dual bundle relates to the connection of X4, the Levi-Civita connection of X4. So the tangent space of sigma is spanned by the three vectors E0, E1, which is the span of L2 inside of X4, and D1, which is of course the direction given by omega-1. So in particular, if we write E0 and D1 as its horizontal lift plus the arrow terms, and the arrow terms are precisely given by these formulas here, then this is going to make the computations much easier. And this is the same reason why we did, this is exactly what we did in the case B equal to 1 in a 3 times R4. Now, by the formula here for rho I, what you can check is that these 2 rho 3 E0 are actually terms involving the second fundamental form of your submanifold of X4. This is just a very easy proof. Just plug in E0 and see what it's telling you. This is just a consequence of Cartan's formalism. So what we need to prove now is that star phi of the tangent space is equal to 0, and this is equivalent to say that the second fundamental form in the direction 0 traced over the base A0, E0, E1, E1 is 0, and the same for the trace of the second fundamental form in the N1 direction. which is nothing but saying that L2 is minimal. And this is just a direct computation, because E0 is equal to this formula here, E1 is equal to this formula here, and the partial one is just partial one. So if we plug in these three vectors in star phi, what you get is precisely minus A1 U square V, and these two terms here that, and so in particular, they imply that the first term is 0 and the second term is 0. And so in particular, we are minimal. Any questions on this proof? Okay, so I'll just move forward, I guess. So similarly to this case, we can think about the negative spinor bundle of S4, and using the so-called Clifford multiplication, which is some geometrical object which the spinor bundle of some manifold has, then we can split the spinor bundle into two over a surface to two subbundles, S plus minus minus. It doesn't really matter the definition of these spaces, but what is important is that in a similar way, you can prove that such a surface is scaly if and only if the base space is minimal. So once again, if you pick your favorite minimal surface of S4, you can construct Cayley's out of it. So I guess this gives you an additional motivation to study minimal surfaces in spheres so the topic of Jesse's talks. Okay, so if there are no questions on the construction of calibrated submanifolds using vector subbundles, I will turn my attention to the construction of calibrated submanifolds using symmetries. Unless there are questions before I move forward. Okay, so this is the second part of this talk, and it's not really related to the first part. So if you fell asleep at any point, then this is a good moment to wake up. And so the idea is we are given a 7-dimensional G2 manifold and the spin 7 manifold, and these are given with some big automorphism group. And what we want to do is to pick a subgroup H of such an automorphism group, and we want to pick such a subgroup with principal orbit of dimension k. And k is going to be a two-dimensional, three-dimensional, depending whether we want to construct co-associatives or Cayley's or associatives. So now we have the action of H on our 7 or 8-dimensional manifold, and we want to look for calibrated submanifolds that are invariant under this action. So the starting idea is, I mean, at least this is the way I see this, is by this orbit type stratification theorem, and by the principal orbit type theorem that I discussed on Tuesday, my manifold roughly, or like the orbit space of my manifold roughly looks like this. So we have in gray a big principal part, which is an open-dense set of my orbit space, and I have some strata, S1 over H, S2 over H, and S3 over H, which are these are the strata of my stratification theorem, and are characterized by being lower dimensional and having some bigger isotropy group. So now the goal is to find a path in such a orbit space so that when we pull back to the total space, so when we pick essentially the action of the group by this curve gamma, what we obtain is a calibrated submanifold. So the idea is you're picking an orbit, so a point in the orbit space, and the pullback of this point is an orbit, and we pick a path of orbits, and this is a k plus one dimensional submanifold, and so it makes sense to try look for calibrated submanifolds in this way. So the crucial observation, and it's going to be even more crucial tomorrow, is that under mild topological assumptions, or mild assumptions on the orbits, more correctly, then you can always find a local gamma passing through any point or any orbit. And this is because if my orbit is k minus one dimensional, or k dimensional, and I'm looking for something that is k plus one dimensional, I have the local existence and uniqueness theorem by Harvey and Lawson, and so I can locally construct such a path. I mean, this construction is implicit, it's just given you by the theorem. But this is the idea. So any question on this idea, on this general way of constructing calibrated submanifolds? I'm going to come back to this tomorrow as well. Okay, so the trivial example is essentially something we already seen. So we are working on S3 times R4, and the subgroup that we are considering is SP1, which sits into in SP1 times SP1 times SP1 just by picking the middle piece. And the middle piece is the one that acts on H, which I'm identifying with R4 by left multiplication by quaternions. So if you see S3 times S3, S3 times R4 as S3 times S3 times R plus, what's going on is just I'm acting on the second S3 by left multiplication. And now I need to consider the SP1 invariant submanifolds in there. And these are just given by some path in S3, my S3, and the path in R, where R is my R plus coordinate. Now, the exercise here is to just try to write down what is the tangent space of this N and plug in the tangent vectors to your free form. And what you get is that the image is co-associative if and only if this first term here is constant. And so what you get really is S3 times, so it's a point times R4. Or in other words, the SP1 invariant co-associatives that I've described are just the fibers over a point of S3. And so these are the same submanifolds that I constructed as a vector subbundle in the trivial case. Okay, so this was the easy part. The more challenging parts come from taking, for instance, S3 invariant co-associatives in the Bryan and Salomon manifolds, the one of topology, the anti-self dual two forms over S4. So, so the idea is, okay, we need to take a three-dimensional subgroup of S5, which is my automorphism group, and the one I'm picking is the one sitting inside of SO5 as SO3 times the identity. So if I see R5 as so is R5 as R3 plus R2, then I have SO3 acting on the first R3 and trivially on the R2 terms. But so the steps that I'm going to describe now are the following. So I will first construct some frame compatible with the SO3 action of my ambient manifold lambda 2 minus of S4, and then write down the ODE problem that I need to solve, and I'll tell you how to solve it, and so you get the co-associatives out of it. So if I write R5 as R3 plus R2, then I think this was also described by Jesse at some point this week, but you can write S4 as the points of R3 plus R2 with norm of x squared plus norm of y squared equal to 1. And so x is equal to cos alpha u, and y is equal to sin alpha v, and u and v are just unit spheres of R3 and R2. So what does this mean? Essentially, this means that I can write my S4 as a one parameter family of S2 times S1. So I have a one parameter family from 0 to pi half. And when I'm reaching pi half, the S2 of this family is collapsing. And what I'm left with is a circle. And if I'm reaching 0 from the right, then my S1 bundle, S1 circle is collapsing, and all I get is an S2. So this is a parameterization of S4, which is compatible with the SO3 action, because the SO3 action is only acting on U. Now I can parameterize U and V in spherical coordinates and polar coordinates, and so in this way I have a local orthonormal frame, an open dense chart of my S4, which induces, of course, a orthonormal coframe, and hence a trivialization of my anti-self dual two forms over such a dense chart of S4. Explicitly, you can compute the orthonormal coframe, and this is given by the alpha, cos alpha d theta, sin alpha d beta, and cos alpha, sin alpha d phi. So these are the 4 one forms that we have here. Any question on this parameterization of S4? Okay, yeah, it's very easy. Now we have an explicit formulas for our orthonormal coframe, and so we can compute the connection one forms for the anti-self dual bundles 201, 202, and 203, and they have this explicit formula. You can compute it, and I do suggest, if you're interested, to just compute d of omega and check that d of omega is equal to -2 rho wedge omega, and then you'll see that this equality holds, and so 201, 202, and 203 are indeed the correct one forms. Now, in the usual manner, we have our connection. We can define and describe the vertical one forms and the horizontal one forms, and these are given by this formula. I'm not going to tell you, but C1, C2, C3 are just the differential of the A1 minus rho, where rho is the connection of the anti-self dual bundles times A. And the horizontal one forms are just the pullback of the frame on the base S4. Okay, so now we kind of really need to understand how the SO3 action acts on the anti-self dual two forms. So We know how it acts on S4 very well, and we now want to understand how it acts on the total space. And you can check that omega 1 is given by this formula here, and this is straightforward from B0. If you do B0 wedge B1 and minus B2 wedge B3, you precisely obtain this formula here. And now alpha and beta, it's easy from the definition to see that they are invariant under the SF3 action. And so the only terms that depend on the SF3 action are sin theta d theta wedge d phi, but this is the volume of the S2 sphere in R3, and so it's invariant under the SF3 action. And hence the whole omega 1 is SF3 invariant. So what we are left to compute is to compute how the SF3 action acts on omega 2 and omega 3. And what you can check is that this SF3 action rotates omega 2 and omega 3. So in other words, to put how this action works in a table. So you can see that if I'm away from a half, and pi a half is the point where my S2 in the base collapses. If I'm away from there, I have two phenomenon. So I'm either these second square root of a2 square plus a3 square doesn't vanish, and then I'm in the principal orbit case, and so my orbit is SO3. Otherwise, if it does vanish, then the action is only acting on the base, and so S3 acting on S4 is as orbit diffeomorphic to S2. Now, if I'm on at pi half, then you can check that the action is just the standard action of S3 on R3, and so I'm either a sphere if I'm away from the 0, or I'm a point if I'm at 0. Okay, any questions on this action, on how this action works? Okay, so I guess I can move forward. So I told you now that we have an SF3 action on S4, and I've adapted my frame of S4 such that it is compatible with my SF3 action. And now we do the same on the fibers. So instead of picking a 1, a 2, and a 3, I know that my SF3 action is giving you a rotation of omega 2 and omega 3, and so it makes sense to write a 2 and a 3 as S cos gamma and S in gamma. So in other words, what's going on here, I have gamma and theta and phi are coordinates for my SF3 action, and the sigma 1, sigma 2, sigma 3 are the standard coframe of SF3. And this is something you can check by computing the sigma 1 and sigma 2 wedge sigma 3 and cyclic permutations of that. Okay, so in this nice open dense set of my manifold, I can write down explicitly my free form, and this free form is this here. I know it doesn't look great, but it doesn't look even that bad. It's just 4 terms, exactly as many as we had at the beginning of all these computations, and it involves all the frame and co-frame that we want. So now we want to construct SO3 invariant associatives. Let me recall you that if you spaced out for a second. And what we've done was to construct these local coordinates on a dense patch of the anti-self dual bundle of sphere. And these coordinates are alpha, beta, Ts and theta phi gamma. And theta phi gamma really parameterize the SO3 orbits. So what we are looking for is a curve in alpha, beta, T, and S. So my four-dimensional SO3 invariant manifold looks like cos alpha U sin alpha V, T tau, S tau, cos gamma, S tau sin gamma. And so in particular, what you can convince yourself in a second is just that the tangent space of N is spanned by the dual frame of sigma 1, sigma 2, sigma 3. And this is because of the observation that we had before, but also by alpha dot d alpha plus beta dot d beta plus S dot ds plus T dot dt. And so it's easy, we can just plug in the dual frame of sigma 1, sigma 2, sigma 3, which is sigma tilde 1, sigma tilde 2, sigma tilde 3. And what you obtain is exactly these equations here. So the first one is a reality check in the sense that if this doesn't vanish, then we cannot expect SO3 invariant associatives. Luckily, it does hold. So then if you plug in sigma tilde 1 and sigma tilde 2 with your V here, what you get is beta constant. And if you do the same with sigma 1, sigma 3, and V, then you get the second term to be constant, and the last one tells you that the third term needs to be constant. So from the point of view of system of ODEs, we found three first integrals of your system, and so this is a fully integrable system of ODEs. So given such a fully integrable system of ODEs, what you can do is consider a map from your 7-dimensional manifold into R3, which is the continuous extension of the obvious map defined on our chart. So I have my 7 coordinates here, and I'm mapping them to U, V cos beta, V sin beta. So U is the first term, sorry, the third term that was preserved by the ODE system, and V is the second one, and beta was the first one. So this is the fibers of this map are smooth co-associatives, and you can check that the topology of such co-associatives is T star S2. Now and the reason is because we have a family of SO3 that is collapsing to an S2, and so it collapses smoothly, and so the only topological manifold that you can get is this one. Now, the singular fibers that we obtain are the one on this sphere, on this circle here, and these are conically singular with topology. These are plus times RP3. Any questions? Okay, so this was the theorem of Jason and Spiro, and it was previously proven by Kotaro in 2013. Good. In the last 5 minutes that I have, I will try to convince you that you can do something similar for Cayley's, even though it's much more complicated. I would not much more complicated, but it's a bit more complicated because everything you need to work with spinors quite heavily. So what I did was I'm looking for three-dimensional submanifolds of sp2 times sp1. So I first look at three-dimensional submanifold of sp2, and the way to look at them is by considering three-dimensional subgroups of SO5. And these are, for instance, SO3 times identity or SP1 times identity, where it is exactly the same group considered by Jason and Spiegel. And this is the group that acts by left multiplication by quaternions on H plus R. Now, the point is that SO5 is double covered by sp2. Indeed, sp2 is another way to say that that's spin 5. And sp1 is a double cover of SO3. So you can construct such a commutative diagram and this other commutative diagram. And these are the two subgroups that I'm considering inside of sp2 times sp1. And the last one is the trivial one, so I'm leaving the base alone and just acting on the fiber. So these are the three subgroups, three-dimensional subgroups that I'm considering. Now, as in Jason's and Spiegel's paper, what we need to do is to understand the group action first. It was a trivial step in Jason's and Spiegel's paper, but here is a little bit more involved, because we have to understand how the lift of subgroups lift to the double cover. And then, as in their paper, we have to find a coframe which is compatible with a group action and solve the ODEs. These steps are very similar, are just more involved computationally. Now, the third case is the trivial one. Indeed, we're just taking the sp1 action on the fiber, and we said that the fibers are Cayley's, and so we recover exactly the same thing as in S3 times R4. The non-trivial cases are the first one and the second, and what we obtained was that we can find an explicit map exactly as in Jason's and Spiegel's paper from the negative spinor bundle of S4 into S4 this time, and the fibers of this map are sp1 invariant Cayley's, and the topology is either S3 times R or R4 or this bundle over CP1, line bundle over CP1. So the point is that the non-vertical fibers that are topologically R4s, that are represented by this line here in green, they are conically singular, and they essentially separate the two different topological type of Cayley's that you can get. Now, in the second result, so for the second group action, now we still have a projection map from the negative spinor bundle of S4 into S4, but now this is implicitly defined. So essentially, we couldn't find all the first integrals of the ODE, and such a implicitly defined map has fibers that are sp1 invariant Cayley's, and topologically we get again S3 times R, or we get R4, but also we get the zero section, and so these are all smooth, and this is a kind of a picture depicting the Cayley's in this context. Okay, I think I've said what I wanted to say today. Tomorrow is going to be more abstract, less computations, and more ideas, I guess, and it's going to be based on my work with Ben. And this is it. Thank you for your attention.
All right, thank you very much. Any question? So all the calibrated submanifolds you find are compact or
No, very so the only compact calibrated submanifolds that you can find in Brian and Salomon are just the zero section.
okay, all right.
And the reason is with Cyan 1 paper that I mentioned half an hour ago. And it's essentially saying that if you take the function that's the distance from the zero section,
Okay.
this is a one convex function. And so if you pick a submanifold which is not contained in the zero section, you have a barrier. I don't know if you're familiar with barrier arguments, but essentially in other ways, if you run in curvature flow, then you have something that it's going to violate the avoidance principle.
Oh.
So that's the idea.
All right, yeah, let's think about it. Thank you very much. Any other question? Thank you very much for the nice talk.